Picture this: a faint glow, invisible to our eyes, stretching across every corner of the sky. It's the oldest light in the universe, a whisper from the dawn of time itself. This is the cosmic microwave background, or CMB, the afterglow of the Big Bang. And yet, despite being one of the most studied phenomena in all of science, it's hiding secrets that keep cosmologists awake at night. What if I told you this ancient light holds clues to not just how the universe began, but to mysteries so profound they could rewrite everything we think we know about reality? Think about that for a second. This isn't just some distant astronomical curiosity, it's a cosmic snapshot, frozen in time from when the universe was just 380,000 years old. The CMB is like finding the first heartbeat of existence, a relic from the moment the universe cooled enough to let light travel freely for the first time. And yet, the more we learn, the more questions pile up. Strange anomalies in its temperature, unexplained patterns in its radiation, even hints of something lurking beyond the edges of our observable universe. All of it suggests there's far more to this story than we've uncovered so far. That's what makes the cosmic microwave background so thrilling. It's not just a fossil, it's a puzzle box packed with 25 unsolved riddles that challenge the very foundations of physics. From the bizarre cold spot that defies explanation to the way the universe's expansion doesn't quite match our predictions, each mystery is a doorway to something deeper. Could the answers lie in undiscovered dimensions, in parallel universes, or in forces we haven't even dreamed of yet? That's the journey we're about to take together. One that will stretch your imagination to its limits and leave you seeing the night sky in a whole new light. Because when it comes to the CMB, the more we learn, the more we realize how much we still don't know, and that's where things get really interesting. One of the most baffling puzzles hidden within the cosmic microwave background is something called the horizon problem. Here's why it keeps scientists up at night no matter where we look in the sky. The CMB's temperature is almost exactly the same, varying by less than 100,000th of a degree. At first glance, that might not sound strange until you realize just how vast those distances really are. Regions of space that appear on opposite sides of the observable universe today were so far apart in the early cosmos that, according to the standard Big Bang model, they should never have had time to exchange heat or reach the same temperature. Think of it like 2 cups of coffee placed at opposite ends of a football field, somehow staying perfectly identical in temperature without ever being connected. How could these regions possibly sync up? This is where things get really interesting. The Big Bang model alone can't explain this uniformity because, based on the speed of light and the age of the universe, those distant patches of space shouldn't have been able to communicate or balance their temperatures. That's the essence of the horizon problem. They weren't just far apart, they were beyond each other's cosmic horizons. It's as if the universe somehow coordinated itself on a scale that defies conventional physics. To solve this, scientists proposed something radical: cosmic inflation. Imagine the universe in its first fraction of a second, expanding faster than the speed of light, stretching out from something unimaginably small to the vast cosmos we see today. This inflationary burst would have smoothed out any temperature differences, leaving behind the eerily uniform CMB we observe now. While inflation answers the horizon problem beautifully, it also opens up new questions. What triggered this hyper-expansion? Could there be evidence of it hidden in the CMB's subtle patterns? And if inflation didn't happen, what's the alternative? The horizon problem isn't just a quirk of the cosmos, it's a glaring clue that our universe still has secrets to spill. Now, let's zoom in on one of the most unsettling oddities in the cosmic microwave background, the so-called cold spot. Picture a vast, eerie patch of sky stretching over 1 billion light-years wide, where the temperature dips just slightly but noticeably below the rest of the CMB's near-perfect uniformity. At first glance, it might not sound like much, After all, we're talking about a difference of just 70 microkelvins, faint enough to miss without precise measurements. But here's the catch: statistically, this kind of anomaly shouldn't exist. The CMB's fluctuations are supposed to be random, like static on an old television screen. Yet this cold spot stands out like a deliberate smudge on an otherwise flawless canvas. So what could possibly explain it? The leading theory points to a cosmic supervoid, an unimaginably vast, empty region of space where galaxies and matter are strangely absent. If light passes through such a void, it loses energy, stretching to longer, cooler wavelengths, an effect known as the integrated Sachs-Wolfe effect. But there's a problem: the cold spot is too cold. Even the largest known supervoids can't account for such a drastic temperature drop. It's like trying to explain a deep freezer with a slightly open window. The numbers just don't add up. That's where things get truly wild. Some physicists have dared to suggest an even more radical explanation: that the cold spot might be a bruise, a remnant of a collision with another universe. In certain multiverse theories, alternate universes could exist in higher dimensions, brushing against our own like soap bubbles in a cosmic foam. If one of these bubbles ever grazed ours during the early universe, it might have left behind a telltale chill in the CMB. It's an electrifying idea, but here's the twist: even this hypothesis struggles to fully explain the cold spot's exact size and temperature profile. So where does that leave us? With a mystery that refuses to fit neatly into any box. Whether it's a statistical fluke, a gap in our understanding of voids, or evidence of realities beyond our own, the cold spot taunts us with possibilities. It's a reminder that the universe, even in its oldest light, still holds shadows we can't yet illuminate. And that's what makes it so fascinating, not just as a scientific puzzle, but as a beacon, drawing us toward the next great cosmic revelation. Just when we thought the cosmic microwave background couldn't get any stranger, along comes something so peculiar that scientists nicknamed it the axis of evil. This isn't some sci-fi plot. It's a real, spine-tingling oddity in the CMB's temperature fluctuations that seems to point in a specific direction. Imagine rolling dice and getting sixes lined up in a perfect row over and over. Statistically, it shouldn't happen, yet that's exactly what the universe appears to be doing with its oldest light. At the heart of this mystery is something called the cosmological principle, the idea that, on large scales, the universe should look the same in all directions, with no preferred axis or special point. It's the foundation of modern cosmology, the reason we assume the laws of physics work the same everywhere. But the axis of evil throws a wrench into that assumption. The CMB's fluctuations aren't as random as they should be. Instead, they show a peculiar alignment along a particular plane in space, almost as if the universe has a hidden tilt. Now, here's where it gets really controversial. Some researchers argue this could just be a statistical fluke, a cosmic coincidence in the data. After all, when you're mapping something as vast as the CMB, anomalies are bound to pop up. But others think it might be evidence of something far more profound. Could this alignment be a fingerprint of an ancient structure that predates the Big Bang itself? One wild theory suggests that our universe might have collided with another in the unimaginable chaos before time began, leaving behind a directional imprint in the CMB. Or perhaps it's a sign that the universe isn't as uniform as we thought, that on the grandest scales, there's a hidden asymmetry governing everything. Either way, the axis of evil isn't just a quirky name. It's a direct challenge to our most fundamental ideas about how the cosmos works. And until we crack its code, it stands as one of the most tantalizing and unsettling enigmas written in the universe's first light. If the universe had a personality, it would be the kind that keeps you guessing. Just when cosmologists thought they had the cosmic microwave background figured out, another curveball appears, one that shakes our understanding of the universe's structure to its core. It's called the missing large-scale anisotropies problem, and it's as counterintuitive as it sounds. Here's the puzzle. when we examine the CMB's temperature fluctuations on the larger scales, patterns stretching across billions of light years, the cosmos seems suspiciously smooth. Too smooth, in fact. According to our best models of cosmic inflation and structure formation, the early universe should have left behind more pronounced wrinkles in spacetime at these vast scales. Think of it like tossing a handful of pebbles into a pond and expecting big waves, only to find the water eerily calm. This isn't just a minor discrepancy. It's a gaping hole in our understanding of how the universe evolved. Some scientists argue it might hint at something profound about the universe's shape, its topology. Could space be curved in ways we haven't detected, like a hall of mirrors on a cosmic scale? If the universe is finite but unbounded, a bit like the surface of a balloon, it might explain why large-scale fluctuations appear muted. Then there's the wilder possibility that unknown physics in the early universe suppressed these anisotropies entirely. Imagine a force or particle long faded from existence that acted like a cosmic iron, smoothing out spacetime's wrinkles before they could imprint on the CMB. Some theories even suggest that gravity itself behaved differently in those first moments, warping the fabric of reality in ways our equations can't yet describe. But here's the twist: the absence of these large-scale patterns isn't just a missing piece of the puzzle. It's a clue that the puzzle might be bigger than we thought. If the universe is hiding its true topology, or if our laws of physics break down at scales we've never probed, then every assumption we've made about cosmic evolution could be up for revision. The CMB's smoothness isn't just a curiosity, it's a silent challenge daring us to look deeper. And that's what makes this mystery so thrilling. It's not about what we see in the ancient light, but what we don't see. And sometimes the gaps in the map are where the real adventure begins. Among all the quirks hidden in the cosmic microwave background, few are as head-scratching as the quadrupole moment anomaly. Think of the CMB's temperature fluctuations like ripples on a pond, some big, some small, each telling a story about the universe's infancy. Scientists chart these ripples using something called the power spectrum, which ranks them by size. The quadrupole moment represents the second largest of these fluctuations, a fundamental heartbeat in the cosmic background. But here's the catch: it's weaker than it should be, so much weaker that it defies our best predictions. At first glance, this might seem like a minor statistical hiccup, but it's anything but. The standard model of cosmology, backed by decades of data, expects these large-scale fluctuations to have a certain strength. Instead, the quadrupole is eerily subdued, as if something or someone turned the volume down on this particular cosmic frequency. The odds of this happening by random chance are astronomically low, like flipping a coin 100 times and getting tails every single time. So what's behind this strange quiet? One possibility is observational bias, some flaw in how we're measuring the CMB. Maybe our instruments are missing a piece of the puzzle, or foreground interference from the Milky Way is muddying the signal. But even after accounting for these factors, the anomaly persists, gnawing at the edges of our understanding. Then there's the more tantalizing option: exotic physics. Could the quadrupole's weakness be a clue to phenomena we haven't yet discovered? Some theorists suggest it might point to a pre-Big Bang phase, an era before time as we know it began, where the universe's initial conditions were set in ways we can't yet model. Others speculate about cosmic topology, where the shape of space itself, like a hall of mirrors on a universal scale, suppresses certain fluctuations, but the most mind-bending idea: that our observable universe is just a tiny patch of a far grander cosmos, and the quadrupole anomaly reflects the gravitational tug of structures beyond our cosmic horizon. Imagine standing in a room with walls so distant you can't see them, but their presence subtly warps the air around you. If true, it would mean the CMB isn't just a relic of our universe's birth, but a window into something infinitely larger. For now, the quadrupole moment remains a whisper in the data, a quiet challenge to our models. Whether it's a cosmic oversight or a sign of deeper truths, one thing's certain: the universe loves keeping secrets. And every anomaly we uncover, it's another invitation to look closer. If you thought the quadrupole moment was puzzling, wait until you meet its cosmic cousin, the octupole moment. Like the quadrupole, it represents another set of large-scale fluctuations in the cosmic microwave background, but with a twist. These two seemingly independent patterns appear to be aligned in a way that defies statistical expectations. Picture two roulette wheels spinning side by side, each landing on the same number over and over again. The odds of that happening by chance vanishingly small. Yet that's essentially what we're seeing in the CMB. This alignment between the quadrupole and octupole moments isn't just a minor curiosity. It's a potential crack in the foundation of modern cosmology. According to the standard model, these fluctuations should be random, with no preferred direction or correlation. Instead, they seem to whisper of a hidden axis, a subtle directionality woven into the fabric of the universe. Some researchers have even dubbed this the axis of evil's shadow, as if the cosmos is winking at us with another layer of mystery. So what could explain this eerie synchronicity? One possibility is that we're seeing the fingerprints of an anisotropic universe, one that isn't perfectly uniform in all directions. Imagine blowing up a balloon with tiny irregularities in its rubber. As it expands, those flaws might stretch into specific patterns. If the early universe had even a slight preference in how it expanded, it could leave behind these aligned moments in the CMB. But then there's the more radical interpretation, that this alignment hints at something beyond our observable universe. Could the gravitational pull of an immense, unseen structure like a supercluster of galaxies so vast it lies beyond our cosmic horizon be tugging at spacetime, leaving this ghostly signature in the CMB? It's as if we're seeing the shadow of a colossus, something so enormous it bends the rules of the game. Of course, skeptics argue this could all be a trick of perspective, an artifact of how we're interpreting the data, or a quirk of foreground interference. But each time scientists reanalyze the measurements, the alignment persists, stubbornly refusing to fade into statistical noise. Whether it's a flaw in our models, a glimpse of the universe's true shape, or a door to something far stranger, one thing's clear: the cosmos is nudging us to look harder. And if history's taught us anything, it's that when the universe whispers, it's usually hiding a shout. One of the most intriguing absences in the cosmic microwave background isn't something we've found, it's something we haven't. According to certain theories of cyclic cosmology, the universe doesn't just have one big bang in its history, but undergoes endless cycles of expansion and contraction like a cosmic heartbeat. These models predict that each cycle should leave behind faint, concentric rings in the CMB, echoes of collisions between universes or previous iterations of our own. So where are they? The search for these giant rings has turned up empty, and that silence speaks volumes. Imagine tossing a stone into a pond and expecting ripples, only to watch the water remain perfectly still. That's the puzzle cosmologists face. If the universe truly recycled itself, these rings would be imprinted like tree rings, marking each rebirth. Their absence doesn't just challenge cyclic models, it forces us to reconsider some of the boldest ideas about reality's origins. But why would these rings matter in the first place? Think of them as cosmic fingerprints. In a cyclic universe, each cycle would stretch and compress space-time, leaving behind subtle patterns in the CMB's temperature fluctuations. Some theories even suggest these rings could reveal collisions with neighboring bubble universes in a vast multiverse. The fact that we don't see them doesn't necessarily disprove these ideas, but it does demand creative explanations. Maybe the cycles erase their own traces, or perhaps the rings are too faint for our current telescopes to detect. Then there's the bigger implication. If the universe isn't cyclic, what does that mean for alternatives? The lack of giant rings leans weight toward the idea of a singular, inflationary Big Bang, a one-time event with no predecessors, but even that conclusion comes with its own mysteries. Without cycles, what set the initial conditions for our universe? Why does it appear so finely tuned for life? The missing rings might feel like a dead end, but they're really a fork in the road, pushing us toward deeper questions about whether our cosmos is alone, recycled, or something stranger entirely. For now, the CMB's smooth canvas remains unmarked by these theoretical rings. Whether that's a clue or just a cosmic red herring, it reminds us that sometimes what we don't see shapes our understanding as much as what we do. And in a universe full of mysteries, absence can be the most tantalizing evidence of all. The universe is supposed to drift apart in a predictable cosmic ballet, galaxies receding from one another in all directions, except for one baffling exception. Astronomers call it the dark flow, and it's exactly as unsettling as it sounds. Imagine gazing at hundreds of distant galaxy clusters, each containing thousands of galaxies, and noticing something impossible. They're all streaming in the same direction, pulled by an unseen force at staggering speeds of nearly 2 million miles per hour. What could possibly be yanking entire clusters off course? This isn't just a statistical blip. The dark flow was first detected by studying subtle distortions in the cosmic microwave background specifically, the way these galaxy clusters subtly warp the CMB's light as they move. It's like watching leaves floating downstream, only to realize every single one is being tugged by an invisible current. The strangest part, this motion points toward a patch of sky with no known supercluster, no colossal mass to explain such a gravitational pull. In fact, the source seems to lie beyond the edge of our observable universe. Now hold that thought. According to everything we know, nothing outside our cosmic horizon should influence matter inside it. Space's expansion should prevent gravity from reaching across that boundary, like a runner trying to grab an apple from a tree that's sprinting away faster than their arm can stretch. Yet the dark flow suggests something out there is breaking the rules. Theories abound. Some physicists argue it might be the gravitational echo of an ancient collision with another universe, a cosmic neighbor brushing past ours in the multiverse's foam. Others propose an even wilder idea, that our universe is embedded in a higher dimensional space, and structures in that realm are tugging on us like magnets beneath a table. Skeptics, of course, counter that the dark flow could be an artifact of incomplete data or measurement errors. But even after multiple independent studies, including NASA's meticulous WMAP and Planck missions, the signal refuses to disappear. What's at stake here isn't just a few rebellious galaxies, it's the integrity of our cosmic map. If the dark flow is real, it implies the universe isn't just stranger than we imagined, it's stranger than we can imagine. Are we being pulled toward an unfathomable structure we'll never see? Or is this a glitch in the matrix, a flaw in how we interpret gravity itself? One thing's certain, until we crack this enigma, the dark flow remains a ghost in the machine, whispering that our universe's story is far from complete. There's something unsettling about the cosmic microwave background when you split it down the middle, because the universe, it turns out, isn't playing fair. The northern and southern hemispheres of the CMB aren't identical twins. They're more like distant cousins, with one side noticeably warmer than the other. This is the hemispherical asymmetry, a cosmic imbalance that shouldn't exist if the early universe was as smooth and uniform as our textbooks claim. Let's put this into perspective. Imagine baking a cake where one half rises perfectly while the other stays oddly flat, even though you use the same batter and oven. That's essentially what we're seeing here, a universe that, on its grandest scales, seems to have favored one direction over another. The temperature difference is subtle, just a fraction of a percent, but in the finely tuned realm of cosmology, even tiny deviations can signal something monumental. So what could cause such a lopsided universe? One leading theory suggests that inflation, the universe's explosive growth spurt, might not have been perfectly even. Picture blowing up a balloon with a weak spot. one side stretches more than the other, leaving behind an irregular shape. If space-time expanded faster in one direction during those first moments, it could have imprinted this asymmetry into the CMB like a cosmic fingerprint. But there's a wilder possibility lurking in the data, that the asymmetry isn't just a quirk of inflation, but evidence of something far more profound. Some theorists argue it might reflect an ancient inhomogeneity, a primordial lumpiness in the fabric of reality itself. Imagine the universe not as a perfectly mixed soup, but as a simmering pot with denser patches here and there. If true, it would mean the Big Bang wasn't the pristine, uniform event we've long assumed, but something messier with regions of higher and lower density from the very beginning. Then there's the elephant in the room. Could this asymmetry be a glimpse beyond our cosmic horizon? If our observable universe is just a tiny bubble in a vast multiverse, neighboring universes might exert gravitational tugs, warping our CMB like invisible hands pressing on a curtain. It's a radical idea, but the hemispherical asymmetry fits uncomfortably well with models where our universe isn't alone, just one piece of a puzzle we're only beginning to assemble. Of course, skeptics have their own take. Some argue it's all an illusion, a trick of perspective caused by our own motion through space or interference from the Milky Way's magnetic fields. But even after accounting for these factors, the asymmetry stubbornly remains, like a whisper the universe refuses to let us ignore. What makes this mystery so thrilling isn't just the imbalance itself, but what it implies about our place in the cosmos. If the universe isn't the same in all directions, it challenges the cosmological principle, the bedrock idea that there's no special place or direction in space. And if that's wrong, it forces us to rewrite the story of everything, from how galaxies form to why we exist at all. The CMB's hemispheres aren't just a curiosity, they're a mirror, reflecting back how much we still don't understand about the universe's first moments. And sometimes the most revealing truths come not from symmetry, but from the cracks in the cosmic facade. The cosmic microwave background is often described as a cosmic fingerprint, its patterns etched by the universe's earliest moments. But what if those patterns aren't quite as random as we thought? That's the heart of the non-Gaussianity debate, a quiet revolution brewing in cosmology. According to the Standard Model, the CMB's temperature fluctuations should follow a Gaussian distribution, meaning they're as unpredictable as the static on an untuned radio. Most measurements support this, but there's a catch. Subtle deviations keep creeping into the data, like whispers of a hidden order beneath the chaos. These deviations, if real, could rewrite our understanding of the universe's birth. Imagine rolling a pair of dice thousands of times and noticing that sevens appear just slightly more often than statistics predict. That's the essence of non-Gaussianity, tiny correlations in the CMB's fluctuations that hint at something deeper at work. One possibility, inflation, the universe's exponential expansion, might not have been the smooth, featureless process we've assumed. Instead, it could have been punctuated by violent quantum jitters, leaving behind telltale wrinkles in spacetime. But here's where it gets wild. Some theorists argue these anomalies might be scars from collisions with other universes. Picture the early cosmos as a frothing sea of bubble universes, each inflating in its own pocket of spacetime. If one of these bubbles grazed ours, the collision could have imprinted non-Gaussian fingerprints in the CMB like cosmic bruises. Others propose even more radical ideas like modified gravity, a fundamental rewrite of Einstein's equations, where gravity behaves differently at the universe's largest scales, warping the CMB in ways we're only beginning to detect. Of course, not everyone's convinced. Skeptics point out that these deviations could just be noise artifacts of how we process the CMB data or foreground interference from our own galaxy. The Planck satellite, humanity's most precise CMB mapper, found no conclusive evidence of non-Gaussianity, but the signal lingers at the edge of detectability like a half-heard melody. Future telescopes like the upcoming LightBird mission might finally settle the debate, peering deeper into the CMB's fine-grained structure. What's at stake here isn't just a technicality. If non-Gaussianity is real, it could be the first tangible clue to phenomena beyond our current physics, multiverses, quantum gravity, or forces we haven't even named yet. The CMB isn't just a snapshot of the past, it's a cipher waiting for us to crack its code. And every anomaly, every deviation from the expected is another piece of the puzzle, one that might lead us to the next great cosmic revelation. One of the most perplexing gaps in our cosmic map isn't something we see, it's something we expected to see but didn't. Enter the mystery of the missing supervoids. According to our understanding of the universe's structure, vast empty regions called supervoids, each spanning hundreds of millions of light-years, should leave a distinctive mark on the cosmic microwave background through something called the integrated Sachs-Wolf effect. Here's how it's supposed to work. As light from the CMB passes through these cosmic deserts, it loses energy climbing out of their weak gravitational wells, causing a slight but measurable temperature dip in the background radiation. But when astronomers went searching for these imprints, they found far fewer voids than theory predicts. It's as if the universe handed us a recipe for a dish, only to serve us half the ingredients. This isn't just a case of missing data. The discrepancy cuts to the heart of how we understand dark energy, the mysterious force accelerating the universe's expansion. The integrated Sachs-Wolf effect depends crucially on the balance between gravity pulling matter together and dark energy pushing it apart. If supervoids aren't imprinting the CMB as expected, it might mean dark energy behaves differently than we've assumed, perhaps growing stronger over time or interacting with matter in ways our models don't account for. Imagine blowing up a balloon with holes that mysteriously shrink as it expands. That's the kind of twist we could be dealing with, but the plot thickens. Some cosmologists argue the problem isn't with dark energy at all, it's with the voids themselves. What if these cosmic empty spots aren't as empty as we think? Simulations suggest supervoids might contain faint, diffuse galaxies or hidden dark matter structures that subtly alter their gravitational pull, masking their true impact on the CMB. Others propose more radical solutions, like modified gravity theories where the laws of Einstein's relativity break down on the largest scales, rendering the Sachs-Wolf effect weaker than predicted. Then there's the observational challenge. Mapping supervoids is notoriously tricky. Their boundaries are fuzzy, and their sheer size makes them hard to catalog. It's like trying to count craters on the moon using only a magnifying glass. You're bound to miss a few. But even accounting for these limitations, the shortage of observed voids remains stubbornly large. Could it be that the universe's structure formed differently than we thought, with matter distributed in ways that leave fewer sprawling, empty regions? Whatever the answer, the missing supervoids aren't just a census problem. They're a potential clue that our cosmic blueprint, the delicate interplay of dark matter, dark energy, and gravity, might need revisions. Every unexplained gap in the data is an invitation to look deeper, to question assumptions we've long taken for granted. And in a universe full of shadows, sometimes what we don't find shines the brightest light on what we still need to learn. Among the many riddles etched into the cosmic microwave background, few are as statistically unnerving as the low L multipole controversy. Imagine tuning a cosmic radio, expecting to hear a symphony of distinct notes across all frequencies, only to discover the deepest bass notes are barely audible. That's essentially what's happening with the CMB's largest scale fluctuations, where the low L multipoles the broadest ripples in spacetime's fabric show strangely subdued power. These aren't just minor discrepancies, they're gaps in the universe's opening chord, missing energy where our models insist it should be loud and clear. At the heart of this mystery lies a fundamental tension between prediction and observation. According to the standard cosmological model, the universe's initial quantum fluctuations should have seeded these large-scale patterns with a certain statistical strength. Yet when we measure them, the quadrupole L equals 2 and octupole L equals 3 moments, the cosmic equivalents of a drum's lowest beats, are suspiciously faint, the odds of this happening by chance. Less than 1 in 100, it's like shuffling a deck of cards and dealing yourself the same perfect hand twice in a row. So what's damping these primordial echoes? One camp argues it's simply cosmic variance, the statistical noise inherent in having only one observable universe to study. After all, we can't rewind the cosmos and replay inflation to see if these patterns shift. Think of it like flipping a coin 10 times and getting 7 heads, unusual but not impossible. Maybe we're just living in a statistically quiet corner of the multiverse where the dice rolled low for these particular fluctuations. But others suspect something deeper at play. Could systematic errors in our measurements be masking the true signal? Foreground interference from our own galaxy's dust or subtle instrumental biases might be smoothing out the CMB's raw data like static obscuring a faint melody. The Planck satellite team meticulously accounted for these factors, yet the anomaly persisted, whispering that the issue might not lie with our instruments but with the universe itself. Then there's the radical possibility that these missing fluctuations hint at a pre-inflationary signature. If the universe didn't start from perfect uniformity, if there were already wrinkles in space-time before inflation stretched them, they might have cancelled out some of the expected large-scale power. Picture a painter trying to cover a cracked canvas. No matter how thick the new layers, traces of the old fractures might still show through. Or perhaps it's a clue to the universe's topology. If space is finite but wraps around like a hall of mirrors, certain wavelengths of fluctuations could interfere destructively, muting their observed amplitude. It's as if the cosmos is a resonant chamber, and some notes are being swallowed by its very structure. What makes the low L multipoles so tantalizing isn't just their absence, it's what their absence implies. If cosmic variance can't fully explain them, we might be staring at the first cracks in our inflationary paradigm. And if they're real, they could point toward phenomena we've never dreamed of, extra dimensions, quantum gravity effects, or even traces of a universe that existed before our own. For now, these quiet fluctuations remain a cosmic murmur, urging us to listen more closely to the universe's oldest song. The universe is supposed to play fair, no favorites, no biases, no hidden tricks up its sleeve. But when scientists peered into the cosmic microwave background's polarization patterns, they stumbled onto something that shouldn't be there, a strange preference for certain twists in the light's orientation, as if the cosmos itself had a handedness. This is the mystery of parity violation in the CMB, and it's as baffling as finding a perfectly symmetrical snowflake that inexplicably spirals only clockwise. To grasp why this is so unsettling, picture flipping the universe in a mirror. Most physical processes like gravity or electromagnetism should look identical in the reflection. That's parity symmetry, a fundamental rule baked into our understanding of physics. Yet when researchers analyzed the CMB's polarized light, they found an overabundance of either left-handed or right-handed swirls in its fluctuations, depending on the scale they examined. It's like tossing a coin and discovering it lands on heads 90% of the time, defying the very laws of probability. So what could break the universe's mirror symmetry so dramatically? One tantalizing lead points to primordial magnetic fields, colossal, invisible structures woven into spacetime during its earliest moments. These fields, if they existed, could have twisted the CMB's light like a cosmic corkscrew, imprinting a preferred handedness as the universe expanded. But here's the catch. Magnetic fields strong enough to leave such a mark would require exotic physics, possibly even undiscovered particles or phase transitions in the infant cosmos. Then there's the more radical possibility, a new force of nature, certain theories beyond the standard model, like chiral gravity or action like particles, predict parity-violating effects that could subtly twist space-time itself. Imagine the early universe as a turbulent sea where these hypothetical particles acted like invisible currents, tugging the CMB's light into lopsided patterns as it traveled toward us. Of course, skeptics aren't ready to rewrite the textbooks just yet. Could this anomaly be an artifact of galactic foregrounds, the Milky Way's own magnetic fields muddying the CMB signal, or perhaps a systematic error in how we untangle the universe's oldest light from modern interference? The Planck satellite's painstaking analyses suggest the signal is real, but faint enough to keep the debate alive. What makes this enigma so thrilling isn't just the violation itself, but what it implies about the universe's hidden architecture. If parity isn't sacrosanct, it opens doors to phenomena we've never considered, from dark matter interactions that twist space-time asymmetrically to relics of a pre-Big Bang era where left and right weren't just directions, but divergent paths in physics itself. The CMB's polarized whispers might be the first hints of a cosmos far stranger than we imagined, one where even the mirrors lie. Imagine the universe waking up from a cosmic dark age, a time when space was filled with a thick fog of neutral hydrogen, blocking light from traveling freely. Then suddenly something ionized that gas, clearing the haze and allowing the first starlight to shine through. This moment, called reionization, is one of the most pivotal chapters in cosmic history. But when we compare the evidence from the cosmic microwave background to what we know about early galaxies, the timelines don't add up. It's like finding a diary that claims you learned to walk at age 2, while all your baby photos show you sprinting at 6 months. The CMB holds crucial clues about reionization in its polarized light. As the first starlight interacted with free electrons, it scattered in a way that left a distinct swirl pattern, a fingerprint of when and how quickly the universe became transparent. According to the Planck satellite's measurements, reionization likely began around redshift 20, when the universe was roughly 150 million years old and lasted hundreds of millions of years. But here's the problem. When astronomers point telescopes like Hubble and James Webb at the earliest galaxies, they don't see enough stars to explain such a massive ionization effort. These fledgling galaxies, bursting with newborn stars, simply don't have the collective wattage to strip electrons from all that hydrogen so quickly. It's as if we've discovered a forest fire was started by a single match. The energy required just doesn't match the evidence. This discrepancy has led to some radical theories. Could dark matter, the universe's invisible scaffolding, have played a role? Some models suggest that decaying or colliding dark matter particles might have released enough high-energy radiation to kickstart reionization long before galaxies got powerful enough to do the job. Picture a hidden furnace beneath the cosmic floorboards, heating things up from behind the scenes. Others speculate about exotic objects like primordial black holes, evaporating in bursts of radiation, or even quasars so distant they've faded from view, their contributions lost to time. Then there's another twist. What if we're misreading the CMB's polarization data entirely? The signal is incredibly faint, and foreground interference from nearby galaxy clusters or even instrumental noise could be muddying the timeline. Or perhaps reionization wasn't a single, uniform event but a patchwork process, with some regions clearing earlier than others. Think of it like ice melting on a lake, not all at once, but in irregular pockets where the sun hits hardest. The stakes here are enormous. If early galaxies alone can't explain reionization, it means we're missing a fundamental piece of cosmic history, one that could rewrite our understanding of how light first triumphed over darkness. And if dark matter or other exotic phenomena were involved, it would be the first tangible evidence of their influence beyond gravity's silent tug. The CMB's polarized whispers are more than just relics. They're a challenge, daring us to rethink what we know about the universe's fiery adolescence. And until we solve this puzzle, the dawn of light remains one of cosmology's greatest untold stories. some of the universe's most elusive ghosts might be hiding in plain sight, woven into the very fabric of spacetime itself. Cosmic strings, theoretical cracks in reality left over from the universe's fiery birth, are predicted to be thinner than an atom yet denser than a mountain range, stretching across the cosmos like invisible threads. If they exist, these bizarre defects could have left faint scars in the cosmic microwave background, subtle temperature variations or polarization patterns betraying their presence. But despite decades of searching, the CMB remains stubbornly silent. Why haven't we found them yet, and what would it mean if we did? Picture the early universe cooling from an unfathomably hot, symmetric state. As it expanded and cooled, phase transitions occurred like water freezing into ice, but on a cosmic scale. Most transitions would have happened smoothly, but some might have left behind defects, regions where spacetime itself didn't quite stitch together perfectly. These kinks in the cosmic quilt are cosmic strings, hypothetical one-dimensional objects with gravity so intense they could warp light and even time around them. A single string just a kilometer long might contain more mass than the entire Milky Way. So where's the evidence the CMB should bear their fingerprints in two key ways? First, strings moving through space would tug on the primordial plasma, creating sharp, linear temperature fluctuations like dragging a finger through steam and leaving a temporary trail. Second, their immense gravity would bend the paths of CMB photons, imprinting distinct swirls in the polarization patterns. Yet scans of the microwave sky show no clear signatures. Some researchers argue the strings might simply be too faint or too sparse, their signals drowned out by the CMB's natural noise. Others wonder if we're not looking carefully enough, like searching for a single strand of spider silk in a blizzard. There's another tantalizing possibility. Cosmic strings might not behave as we expect. Traditional models assume they're stable, but what if they're dynamic, oscillating wildly or even snapping and reconnecting in ways that erase their own imprints? Or perhaps they're not strings at all, but more exotic defects, walls, knots, or hybrid structures that leave entirely different marks. The truth might require next-generation telescopes like the upcoming Simons Observatory or CMB-S4, with resolution sharp enough to spot the faintest spacetime stitches. What's at stake goes beyond mere curiosity. If cosmic strings are real, they'd offer a direct window into the universe's first trillionth of a second, a time far earlier than the CMB itself can probe. They could also explain anomalies like the dark flow or those mysterious alignments in the CMB's large-scale patterns. Even their absence would be profound, forcing us to rethink how phase transitions shaped the infant cosmos. The hunt for these phantom threads isn't just about finding cosmic cracks, it's about testing whether our universe was woven as perfectly as we've assumed, or if its seams are frayed in ways we've yet to imagine. The cosmic microwave background isn't just a snapshot of the early universe, it's a cosmic thermometer, radiating with near-perfect blackbody spectrum, the kind of heat glow you'd expect from an ideal oven. But what if this thermal fingerprint isn't as flawless as it seems? Hidden within the CMB's smooth curve could be spectral distortions, tiny kinks, or bumps in its energy distribution, whispers of violent events that shook the universe long after the Big Bang's afterglow first appeared. These minuscule deviations, if they exist, might be the only traces of exotic physics, from annihilating dark matter to the death throes of primordial particles. Think of the CMB's spectrum like a musical note played with perfect pitch. Any distortion, a slight sharp or flat, would suggest something interfered with the instrument. In cosmology, those off notes could come from energy injections that heated the cosmic plasma after it had already cooled into neutrality. For example, if dark matter particles collided and annihilated in the early universe, their explosive energy would have dumped heat into the primordial gas, leaving behind a telltale bump in the CMB spectrum. It's like finding scorch marks on a painting, evidence of a fire no one saw. Then there's the possibility of decaying relics, hypothetical particles left over from the universe's earliest moments, slowly disintegrating over eons. As these particles vanished, they'd release energy, subtly warping the CMB's thermal profile. Imagine an ice cube dissolving in a glass of water. Even if you can't see the cube itself, the temperature change betrays its presence. Some theories suggest these relics could be actions, sterile neutrinos, or even remnants of higher dimensional physics. Their decay imprinting spectral fingerprints we're only now learning to read. But hunting these distortions is like listening for a single off-key violin in a symphony hall. The CMB's blackbody spectrum is so precise that deviations would be staggeringly small parts per million or even per billion. Current instruments like the Planck satellite weren't sensitive enough to catch them. That's why projects like PIXI, a proposed next-generation spectrometer, are so exciting. Designed to measure the CMB's spectrum with unprecedented precision, PIXI could spot distortions invisible to earlier telescopes, opening a window into eras of cosmic history we've never probed directly. What makes this search so thrilling isn't just the technical challenge, it's the stakes. Spectral distortions could reveal epochs when the universe was anything but calm. Between the CMB's release and the birth of the first stars, space might have been a battleground for dark matter annihilations, decaying relics, or even primordial black holes evaporating in bursts of radiation. These events would have left no other trace, their light swallowed by the fog of time. The CMB spectrum is our only hope of glimpsing them, and if we find nothing, that silence would be just as profound. A perfectly pristine blackbody spectrum would tighten the screws on exotic physics, forcing us to rethink theories about dark matter's interactions or the existence of certain relic particles. Either way, the CMB's spectral purity, or its hidden flaws, holds secrets we're only beginning to decode. In the quest to understand the universe's hidden chapters, sometimes the smallest deviations speak the loudest. Hidden within the faint whispers of the cosmic microwave background lies a signal so subtle, it could either confirm our boldest theories or send cosmologists back to the drawing board, the elusive B-mode polarization. Picture the CMB's light not just as a blanket of warmth, but as a tapestry of waves, each vibrating in specific directions. Most of these waves, called E-modes, twist in ways that mirror the universe's earliest density fluctuations. But B-modes, they curl like whirlpools, and their presence could be the smoking gun for inflation or a cosmic red herring. Here's why this matters. During inflation, the universe's exponential expansion should have sent ripples through space-time itself, gravitational waves powerful enough to twist the CMB's polarization into these telltale B-mode patterns. Detecting them would be like finding the fossilized footprints of the Big Bang's most violent moment. But there's a catch. The interstellar dust littering our galaxy also scatters light in swirling patterns, mimicking these primordial signals. It's the ultimate case of cosmic counterfeit, a perfect replica hiding the real treasure. The hunt for true B-modes has been a roller coaster. In 2014, the BICEP-2 team thought they'd struck gold with a detection so significant it made global headlines. But further analysis revealed the signal was largely contaminated by galactic dust, a humbling reminder of how nature loves to blur the lines between discovery and illusion. Since then, projects like the Keck Array and Planck have meticulously mapped the dust's interference, peeling back its veil to search for the primordial truth beneath. What makes this enigma so tantalizing isn't just the potential payoff, it's the stakes. If B-modes are ever confirmed, they'd prove inflation happened, locking in a pivotal chapter of cosmic history. But if they remain elusive, it might mean inflation wasn't as violent as we thought, or that entirely new physics govern the universe's birth. Some theorists even suggest alternatives like bouncing cosmologies or string gas scenarios where B-modes would be absent or fundamentally different. Then there's the wild card. What if the dust isn't the only imposter? Primordial magnetic fields or exotic quantum effects could also generate B-mode lookalikes, adding layers to an already dizzying puzzle. Future telescopes like the Simons Observatory are doubling down on sensitivity, aiming to tease apart these confounding factors with precision never before achieved. For now, the B-mode polarization remains cosmology's high-stakes poker game, a bet on whether we're reading the universe's deepest truths or being fooled by its cosmic sleight of hand. Every flicker of data brings us closer to answering one of science's biggest questions. Did the universe really burst into existence in a whirlwind of gravitational waves, or is the story far stranger than we've dared to dream? The universe's earliest moments should have been a symphony of chaos, space itself stretching at breakneck speeds, space-time rippling with gravitational waves powerful enough to leave permanent scars. These primordial tremors, known as tensor modes, were predicted to imprint a specific pattern onto the cosmic microwave background, a ghostly echo of inflation's violent birth. But when scientists went searching for them, they found something startling: silence. The CMB's tensor modes are either far weaker than expected or missing altogether, and their absence is shaking the foundations of our cosmic origin story. Imagine the early universe as a stormy ocean, with gravitational waves churning like massive waves crashing against the fabric of reality. Inflationary theory suggests these waves should have frozen into the CMB's polarization as distinct B-mode patterns, curling like whirlpools in spacetime. Finding them would be the smoking gun for inflation proof that the universe underwent that exponential growth spurt in its first fraction of a second. But the latest data from observatories like BICEP, Keck Array, and Planck tell a different tale. The B-modes we've detected so far can largely be explained by galactic dust, leaving little room for the primordial signal we expected. It's like listening for the roar of a waterfall and hearing only a faint whisper instead. This leaves cosmologists with a dilemma. If tensor modes are truly absent or too faint to detect, some of inflation's most popular models, particularly those predicting a strong gravitational wave background, may need serious revision. It's not that inflation itself is wrong, but the details of how it happened might be far more nuanced than we imagined. Perhaps the inflationary energy scale was lower, meaning gentler ripples in spacetime. Or maybe the process wasn't as uniform, with patches of the universe inflating at different rates, diluting the overall tensor signal. Some theorists are even exploring alternatives, like scenarios where multiple stages of inflation occurred, each leaving different imprints. Then there's the more radical possibility. What if inflation didn't happen the way we think at all? A handful of scientists argue that the missing tensor modes could point to entirely different beginnings, bouncing universes that collapse and rebound, or emergent cosmologies where space and time crystallize from some deeper structure. These ideas are still fringe, but the absence of expected evidence has a way of making fringe ideas harder to ignore. Of course, not all hope is lost. Future telescopes like the upcoming Lightbird mission or the next-generation CMB S4 experiment will probe deeper into the CMB's polarization with unprecedented sensitivity. If primordial tensor modes are hiding just below current detection thresholds, these instruments might finally uncover them. But if they come up empty again, the mystery will only deepen. The missing tensor modes aren't just a gap in the data, they're a question mark hovering over one of cosmology's most cherished theories. Whether they're quietly waiting to be found or forcing us to rewrite cosmic history, their absence reminds us that even the loudest echoes of the Big Bang can sometimes fade into silence. And in that silence, the universe might be hinting at truths we're only beginning to imagine. What if the universe we see is just the surface of something far deeper? The cosmic microwave background might hold clues that our reality isn't the full story, that hidden dimensions, curled up or stretched beyond our perception, could be leaving faint fingerprints in the oldest light we can observe. This isn't science fiction. It's a serious possibility raised by brain-world cosmology and string theory, where our three-dimensional universe could be a membrane floating in a higher dimensional space. And the CMB's oddities, those tiny temperature fluctuations and puzzling alignments, might be the first hints that these extra dimensions are real. Take the axis of evil, for example, that eerie alignment of large-scale fluctuations in the CMB that seems to defy randomness. If space has hidden dimensions, gravitational waves or quantum effects leaking through from those realms could have subtly twisted the early universe, leaving behind directional patterns we're only now detecting. Picture a pond disturbed not just by the wind, but by vibrations from an underground river, one we can't see but whose influence ripples across the surface. String theory takes this even further, suggesting that all particles are tiny vibrating strings moving through 10 or 11 dimensions. Most of these dimensions would be compactified, curled up so tightly we'd never notice them, unless their presence warped spacetime on cosmic scales. The CMB's spectral distortions or polarization anomalies could be the echo of those higher dimensional vibrations, like hearing the hum of a distant engine through a wall. Then there's the brain world scenario, where our universe is a three-dimensional brain embedded in a higher dimensional bulk. If another brain collided with ours during the universe's infancy, the energy released could have left imprints in the CMB's temperature map, perhaps even explaining that infamous cold spot. Think of it like two sheets of paper brushing against each other in a dark room. You might not see the sheets, but the static electricity they generate could light up the shadows. Skeptics, of course, argue these ideas are untestable, that extra dimensions are a convenient mathematical abstraction with no tangible proof. But the CMB offers a rare opportunity. If higher dimensions exist, they'd alter how gravity propagates in the early universe, potentially leaving subtle scars in the microwave background's power spectrum. Future telescopes like CMB S4 could hunt for these deviations, searching for telltale gaps or excesses in the data that defy four-dimensional physics. What makes this mystery so electrifying isn't just the science, it's the sheer audacity of the idea. The CMB, a relic from 13.8 billion years ago, might be quietly whispering that reality is vaster and weirder than we ever imagined. And if those whispers are real, they could rewrite not just cosmology, but our very understanding of existence. The universe has never been one to show all its cards. Why would dimensions be any different? The laws of physics are supposed to be universal, unchanging pillars holding reality together. But what if they aren't as constant as we think? The cosmic microwave background might be hiding a bombshell. Subtle variations that suggest the universe's fundamental constants, like the fine structure constant governing electromagnetism, could have shifted over cosmic time. It's a claim that challenges everything from textbooks to our understanding of reality itself. At first glance, the idea seems absurd. The fine structure constant, a number that dictates how light and matter interact, has been measured in labs with incredible precision. Change it even slightly and atoms wouldn't bond, stars wouldn't shine, and life as we know it would be impossible. Yet when astronomers analyze light from distant quasars, some of the oldest light in the universe, they've found tantalizing hints that this constant might have been different billions of years ago. The discrepancies are tiny, just parts in a million, but if real, they'd rewrite physics. Now, here's where the CMB comes in. If constants like the fine structure varied in the early universe, they'd leave imprints in the microwave background's temperature and polarization patterns. Think of it like baking a cake with slightly different ingredients each time. The final product would bear subtle but telltale differences. Specifically, a changing fine structure constant would alter how hydrogen and helium formed during the universe's first few minutes, shifting the ratios of these elements and leaving faint fingerprints in the CMB's power spectrum. The challenge: these signals are buried under layers of cosmic noise. Detecting them would require combing through the CMB's data with unprecedented precision. teasing apart the effects of varying constants from other cosmological quirks. Some researchers argue that anomalies in the CMB's large-scale fluctuations like the quadrupole and octupole moments being weaker than expected might already be hinting at this very possibility. It's as if the universe left breadcrumbs, but we're only now learning to read the trail. Of course, skeptics aren't convinced. Could these anomalies just be statistical flukes or systematic errors in our measurements? After all, the CMB is a minefield of foreground interference, from galactic dust to gravitational lensing. And even if the signal is real, could it be explained by something less radical, like an undiscovered component of dark matter or a shift in our understanding of cosmic expansion? Then there's the elephant in the room. If constants can vary, what's driving the change? One wild theory suggests extra dimensions. Those hidden folds of spacetime predicted by string theory might be slowly unraveling, subtly tweaking the laws of physics as they go. Others propose that dark energy, the mysterious force accelerating the universe's expansion, could be interacting with fundamental constants in ways we don't yet understand. Imagine the universe as a slowly tuning guitar, its strings tightening or loosening over billions of years. For now, the evidence remains tantalizingly out of reach. Future missions like the European Space Agency's Euclid telescope or next-generation CMB experiments could finally settle the debate, hunting for these ultra-subtle variations with instruments sharp enough to cut through the cosmic noise. Until then, the possibility hangs in the air, a whisper that the universe's rulebook might not be as fixed as we thought. And if that's true, it wouldn't just change how we see the cosmos. It would change how we see reality itself. Dark matter is the universe's most elusive architect, invisible, intangible, yet shaping the cosmos on scales we can barely fathom. And while it refuses to interact with light, the cosmic microwave background might be the closest thing we have to a dark matter detective, revealing its fingerprints in ways no telescope ever could. The CMB's temperature fluctuations don't just map the early universe's clumps of ordinary matter, they also trace the gravitational wells carved by dark matter's unseen hand. But here's the twist: the more we learn, the more we realize dark matter might not play by the rules we've written for it. Take the CMB's power spectrum, the cosmic barcode that tells us how matter clustered in the universe's infancy. The peaks and dips in this pattern are exquisitely sensitive to dark matter's properties. Too much dark matter and the peaks would shift one way, too little and they'd lean another. What we've found is a Goldilocks fit for cold dark matter particles that move sluggishly, forming the gravitational scaffolding for galaxies. But there's a catch. While the CMB nails down dark matter's overall abundance, it stays silent on how, or if this mysterious substance interacts with anything beyond gravity. That silence is deafening. If dark matter occasionally bumped into ordinary particles in the early universe, even faintly, those collisions would have left subtle scars in the CMB's polarization patterns. Think of it like hearing echoes in a canyon. If dark matter scattered light or matter, those echoes would carry a telltale distortion. Yet so far, the CMB shows no such fingerprints, suggesting dark matter might be even more aloof than we thought. Some models, like weakly interacting massive particles or WIMP, are hanging by a thread, while others, like sterile neutrinos or actions, are stepping into the spotlight. Then there's the elephant in the room, small-scale structure. The CMB paints dark matter as smooth on large scales, but when we zoom in on dwarf galaxies or galactic clusters, things get messy. Simulations predict a universe teeming with tiny dark matter clumps, yet we don't see nearly as many as expected. Could dark matter be warmer or more interactive than the CMB suggests? Some theorists argue for fuzzy dark matter, particles so light they blur out small-scale structure like quantum waves. Others propose dark matter with a hidden charge, subtly repelling itself and avoiding dense clumps. The CMB's greatest gift and frustration is its restraint. It tells us dark matter exists, how much there is, and even how it shaped the universe's large-scale web. But it refuses to spill the secrets of what dark matter actually is. Future CMB experiments like CMB-S4 might finally catch dark matter in the act, hunting for rare polarization signatures or spectral distortions that betray its interactions. Until then, the CMB remains both our best witness and our most cryptic clue, a cosmic Rosetta Stone we're still learning to read. And in that gap between what we see and what we could see, the universe's greatest shadow waits, daring us to look deeper. One of the most heated debates in modern cosmology starts with a simple number, the Hubble constant, a figure that tells us how fast the universe is expanding right now. You'd think measuring something so fundamental would be straightforward, but here's the twist. When scientists calculate this number using the cosmic microwave background, they get a different answer than when they measure it by observing nearby galaxies. The discrepancy isn't just a rounding error. It's a full-blown crisis, with the CMB's value sitting nearly 10% lower than what local measurements suggest. This isn't just a technical disagreement, it's a cosmic screaming match that might force us to rewrite the rules of the universe. Let's break it down. The CMB gives us a snapshot of the universe at 380,000 years old, a time when matter and radiation parted ways. From that pristine image, cosmologists can extrapolate forward, using our best models of dark energy and cosmic evolution to predict today's expansion rate. The result, around 67 kilometers per second per megaparsec, meaning for every additional megaparsec of distance, space itself stretches 67 kilometers faster every second. But when astronomers measure the Hubble constant directly by tracking the motions of supernova or pulsating stars in nearby galaxies, they consistently land closer to 73. That gap might sound small, but in the precise world of cosmology, it's like two clocks ticking at wildly different speeds despite being built from the same blueprint. So why the mismatch? One possibility is that something's off in our measurements. Maybe galactic dust is subtly skewing supernova brightness, or the CMB's data is being misinterpreted due to unseen foreground effects. But after years of cross-checking, the error bars have only tightened and the tension remains. That's led researchers to a far more thrilling conclusion. Our models might be missing a piece of physics. Imagine baking a cake where the recipe calls for flour, sugar, and eggs, but no matter how carefully you follow the steps, it never rises quite right. The CMB's Hubble tension could be the universe's way of telling us there's an ingredient we've overlooked. What could that missing ingredient be? Some theorists point to dark energy, the mysterious force accelerating the universe's expansion. Perhaps it isn't constant as we've assumed, but evolves over time, stronger in the past or weaker today. Others wonder if dark matter has properties we haven't accounted for. Maybe it interacts with itself or with light in ways that tweak the expansion rate subtly. Then there's the wild card, early dark energy, a hypothetical burst of repulsive gravity that briefly surged during the universe's first few 100,000 years, leaving traces in the CMB while throwing off our modern calculations. But the boldest ideas go even further. Could the Hubble tension hint that gravity itself works differently on cosmic scales? Modified gravity theories, like those that tweak Einstein's equations, might explain why the CMB and local measurements disagree. Or perhaps we're seeing the fingerprints of a multiverse, with our observable cosmos floating in a larger space where the rules aren't quite uniform. It's like living in a valley and assuming the whole world is flat, only to climb a mountain and realize the landscape stretches far beyond what you ever imagined. For now, the Hubble tension stands as one of cosmology's greatest unsolved puzzles, a rift between two ways of seeing the universe, each backed by overwhelming evidence yet refusing to align. Future telescopes like the James Webb Space Telescope or next-generation CMB experiments aim to bridge this gap, hunting for systematic errors or uncovering new physics that could reconcile the numbers. But whether the answer lies in tweaked models, exotic energy, or a fundamental rewrite of cosmology's rules, one thing's certain: the universe is nudging us toward a deeper truth. And sometimes the most profound discoveries begin with a disagreement, especially when the cosmos itself is the one refusing to agree. Among the countless fluctuations in the cosmic microwave background, a handful of peculiar patterns stand out, not random blobs or streaks, but eerily perfect circles stacked like ripples in a pond. These concentric rings, first highlighted by researchers over a decade ago, ignited fierce debate. Could they be scars from events that occurred before the Big Bang itself? The idea sounds like science fiction evidence of a universe that existed before time began, leaving ghostly imprints in our own cosmic dawn. But like all extraordinary claims, these circles demand extraordinary proof, and that's where the controversy begins. Picture the early universe not as a single explosive moment, but as a cosmic reset, a bounce from a previous collapsing phase, or a collision between two higher dimensional membranes in a multiverse. In such scenarios, the energy released would send shockwaves through the newborn cosmos, imprinting concentric temperature variations in the CMB. Think of it like slamming two sheets of ice together. The impact would create circular fractures, frozen in place as the universe expanded. When scientists analyzed the CMB's temperature maps, they claimed to find exactly that: sets of rings where the temperature variations were slightly more pronounced, aligning with predictions of pre-Big Bang physics. But here's the catch: the universe is a messy place, and randomness can mimic order if you look hard enough. Critics argue these circles might just be statistical illusions, the inevitable outcome of poring over a dataset as vast as the CMB. It's like searching for faces in cloud formations. Given enough data, something will appear meaningful by chance alone. To test this, researchers ran simulations creating thousands of fake CMB maps with the same overall properties but no underlying circular patterns. Sure enough, some of these artificial skies contained ring-like structures just as prominent as the real ones. The odds, depending on the study, anywhere from 1 in 50 to 1 in several hundred, unusual but hardly definitive. The debate hinges on a deeper question: what counts as significant in a cosmos this vast? The CMB contains billions of pixels, each with its own subtle variation. Even rare fluctuations are guaranteed to occur somewhere in that sea of data. Proponents counter that it's not just the circle's existence, but their properties that matter: their spacing, their temperature profiles, their alignment with theoretical predictions. Some rings, for example, appear to have a preferred direction, as if marking the axis of an ancient collision. Others overlap in ways that seem to echo cyclical universe models, where each Big Bang is preceded by a big crunch. Yet the Planck satellite, humanity's most detailed CMB mapper, delivered a blow to these claims. Its high-resolution data failed to confirm the rings at the confidence levels needed to upend cosmology. The circles are still there, but their statistical significance crumbles under closer scrutiny, like a sandcastle under a tide. Some researchers haven't given up. They argue that future telescopes with even finer precision might tease out fainter, more elusive patterns. Others suggest the real signal could be buried in the CMB's polarization data, where pre-Big Bang echoes might leave a cleaner fingerprint. What makes this mystery so captivating isn't just the audacity of the idea, it's the reminder that science thrives on the edge of uncertainty. The CMB's circles could be cosmic mirages, fleeting patterns in the noise, or they might be the first whispers of a reality stranger than we've dared to imagine, a universe that cycles through birth and rebirth, or one tangled in a web of higher dimensional collisions. Until we know for sure, these rings linger at the frontier of discovery, tantalizing and ambiguous, daring us to look deeper into the static of the cosmos. Because sometimes the most profound truths begin as imperfections in the data, waiting for someone to connect the dots. The cosmic microwave background should be the ultimate cosmic backdrop, a near-perfect canvas of ancient light. But tilt your head slightly and you'll notice something odd. One half of the sky glows just a fraction warmer than the other. This is the CMB's dipole anisotropy, a temperature difference long chalked up to our own motion through space. As the Milky Way hurtles through the cosmos at roughly 600 kilometers per second, the Doppler effect should compress the CMB's microwaves in front of us, making that region appear warmer while stretching them behind us, leaving the opposite side cooler. It's like running through rain. You'd feel more drops hitting your front than your back. But what if this explanation, tidy as it seems, isn't the whole story? Dig deeper and the numbers start to raise eyebrows. Our measured motion doesn't quite align with the dipole's magnitude or direction when compared to other cosmic reference frames, like the distribution of distant galaxies. It's as if the universe is tugging us toward something beyond the gravitational pull of nearby superclusters. Some researchers argue this discrepancy might hint at colossal structures, vast concentrations of mass lurking beyond our observable horizon, their gravity subtly skewing the CMB's dipole. Imagine floating in a pool and feeling a current tugging you not from the edge you can see, but from something massive hidden beneath the water's murky depths. Then there's the timing problem. If our local motion were the sole culprit, the dipole should perfectly match the CMB's frame. Yet studies suggest the dipole's alignment with the rest of the CMB's fluctuations is oddly lopsided, as if stitched together from two different fabrics. Could this mean part of the signal isn't from our movement at all, but baked into the universe's very structure? One provocative theory posits that the dipole reflects primordial inhomogeneities, regions of higher and lower density left over from the Big Bang itself. In this scenario, the universe wasn't perfectly uniform even in its infancy, and those initial wrinkles might still echo in the CMB's largest scale patterns. Skeptics, of course, have counterarguments. Galactic dust or systematic errors in how we subtract the Milky Way's foreground glow could be muddying the dipole's true signal. Others suggest we might be underestimating the gravitational pull of known structures like the Shapley supercluster, a sprawling mass of galaxies 800 million light-years away. But even accounting for these factors, the anomalies linger, whispering that our cosmic speedometer might be missing a few digits, the most electrifying possibility. That the dipole is a portal, a hint that our observable universe is just a speck in something far grander. If immense, unseen masses lie beyond our horizon, their gravity could be warping space-time on scales so vast they've nudged not just galaxies but the CMB itself. It's a cosmic hall of mirrors where reflections of distant giants might be the key to decoding our own motion. Until we peer deeper into the CMB's finer details or map the universe's large-scale flow with sharper precision, the dipole will remain both a mundane fact and a tantalizing riddle, a reminder that even the simplest cosmic signals can hide profound truth. Right now, the cosmic microwave background hums at a chilly 2.7 Kelvin, a fading whisper from the universe's fiery birth. But this is just a snapshot in time, a single frame in a cosmic movie playing out over trillions of years. As the universe expands, stretching space-time like an infinite rubber sheet, the CMB will continue its slow fade into oblivion. Each passing eon will redshift its photons further, stretching their wavelengths until what was once microwave radiation becomes feeble radio waves, then barely perceptible whispers of infrared, and eventually nothing at all. It's the ultimate fate of the universe's first light, not with a bang but with a quiet, inexorable dissolution into the void. But here's where it gets eerie. Imagine a civilization born 100 billion years from now, in a universe so expanded that all galaxies beyond their local cluster have vanished over the cosmic horizon. Their night sky would be unrecognizable to us, no Andromeda, no Milky Way band of stars, just an inky blackness punctuated by the dim glow of dying red dwarfs. And when they train their telescopes on the empty heavens searching for the CMB, they'd find it 1,000 times colder and fainter than we detect today. By then, its temperature might measure just 1,000th of a Kelvin, its signal so diluted that distinguishing it from pure noise would require technology beyond our wildest dreams. What would such a distant era make of this ghostly echo? Without the context we have, a universe still studded with nearby galaxies and a vibrant cosmic web, they might mistake the CMB for some exotic local phenomenon or dismiss it entirely. The very evidence of the Big Bang, so obvious to us, could become an enigma buried in static. And if dark energy continues accelerating the universe's expansion as expected, even that feeble remnant will eventually redshift beyond detectability. The CMB won't just cool, it will vanish from the observational record altogether, leaving future cosmologists with no direct trace of the universe's explosive beginning. Yet there's a haunting possibility. Civilizations advanced enough might uncover other ways to reconstruct the past, perhaps by studying the relic velocities of ancient star clusters or the faint gravitational waves from inflation. They could piece together a history we're only beginning to grasp. The CMB's disappearance wouldn't erase the universe's origin story, just hide it behind layers of cosmic distance and time. For now, though, we're living in a golden age of cosmic archaeology, where the CMB is still bright enough to read like an open book. Its slow fade is a reminder that the universe's secrets aren't eternal. Some doors close forever, and we're fortunate to exist in an era when so many remain ajar. The question isn't just what the CMB tells us today, but how much of its story will be lost to the abyss of deep time. And that, perhaps, is the greatest mystery of all. From the eerie cold spot that could be a bruise from another universe, to the axis of evil that seems to tilt the cosmos off kilter, these 25 mysteries aren't just gaps in our knowledge, they're portals to entirely new physics. Each anomaly in the cosmic microwave background cracks open a door to something profound. The missing supervoids that defy dark energy's grip, the hemispherical asymmetry suggesting our universe might be lopsided, and the haunting silence of primordial gravitational waves that could rewrite inflation's story. Even the CMB's spectral purity hides whispers of annihilating dark matter or decaying relics from dimensions we've yet to discover. Then there are the deeper enigmas, the dipole anisotropy hinting at unseen giants beyond our horizon, the low L multipoles too quiet for comfort, and the bizarre alignments between quadrupole and octupole moments that mock randomness. And let's not forget the grandest puzzles of all, the Hubble tension tearing cosmology in two, the spectral distortions that could reveal the universe's hidden battles, and those controversial concentric rings that might be echoes of a time before the Big Bang. Every flicker in this ancient light challenges what we think we know, from the constancy of physical laws to the very shape of spacetime itself. What ties these mysteries together isn't just their defiance of explanation, it's their audacity. They refuse to fit neatly into our models, daring us to dream bigger. Maybe the universe isn't uniform, maybe it's not alone. Maybe the rules we hold sacred are just local bylaws in a grander cosmic archipelago. The CMB isn't just a relic, it's a mirror reflecting back how much we still don't understand, and that's why these puzzles matter. They're not dead ends, they're trailheads pointing toward discoveries that could redefine reality. So here's the real question, which of these 25 mysteries grabs you? Is it the dark flow's impossible pull, the parity-violating swirls that break physics mirrors, or the vanishing tensor modes that leave inflation's loudest chorus unsung? Drop your thoughts in the comments, let's geek out over the cosmos' greatest unsolved riddles together. And if you're hungry for more deep dives into the universe's secrets, hit subscribe. Because the CMB's puzzles are just the beginning, and the next cosmic revelation might be one video away.